This is a question that you might have asked yourself while lying on the beach, watching the waves crash into one another only to be pulled back out to sea again and again for eternity. It seems so simple, but it's also deceptively difficult to answer. Why does gravity matter? We've come to rely on gravity to exist in our daily lives. We can safely assume it will always be there, holding down the atmosphere around the Earth, making water flow downhill, allowing us to stand upright without floating away. But if we take a step back and really consider it, we can realize just how exceptional what we experience here on Earth truly is. For example, in order for life to emerge and evolve the way that it has, the planet needs to be just the right size. If it were too big or too small, life would not be able to flourish like it does. And the reason that happens is because of gravity. In this video, we are going to explore why gravity matters. This is a series that explores the fundamentals of physics and mathematics that describe our universe. Each episode will try to answer the great questions of physics by explaining what they are, why we care, and how they work. First, let's think about why we're even asking this question in the first place. That's right. We're re-asking this question because we're about to leave our planet behind and venture out into space. As humans, we tend to get pretty myopic when we focus on our experiences on Earth and assume that they apply to the rest of the universe. But from the perspective of the entire universe, we are extremely limited in our thinking. For example, the fact that we can walk across a field without falling through the ground is actually an extraordinary coincidence. You see, solids are made up of atoms. And if we zoom in on any solid object, like the phone you're watching this video on, you will find that it is a lattice of atoms vibrating back and forth around a central point. The spaces between those atoms is incomprehensibly tiny. Now imagine that you're a subatomic particle and you're close to the edge of an atom. What would happen if you took a step forward? Well, if your step was too far, you would fall into the positively charged nucleus of an atom and get annihilated. But if you took a very small step, then you would simply continue on as before. So really, we can only take steps of a certain size because of quantum mechanics. The exact size of these steps depends on the energy that you have. So the more energy you have, the bigger the steps that you can take. And this means that the structure of solids is very dependent on temperature. When things are cold, atoms vibrate less, and so the distance between them is smaller. Conversely, when things are hot, atoms vibrate more, and the distance between them increases. If something gets too hot, then the distance between the atoms can become so large that the forces holding them together, known as interatomic bonds, can no longer hold. And solids can melt into liquids. If something gets even hotter than that, the atoms will move so far apart that those interatomic bonds can no longer hold either, and liquids can evaporate into gases. So given that walking is only possible because of the particular range of temperatures that we have on Earth, it isn't surprising that this doesn't work on other planets. On Mars, for example, the low atmospheric pressure makes water freeze at a much lower temperature, meaning that it can exist as a solid for much longer. This is why we see giant glaciers on Mars. It's also why rovers need to be built in a way that allows them to drive over large obstacles. But this raises an important question. Why does the temperature on the surface of Mars differ so much from the temperature on the surface of Earth? There are many factors that contribute to this, but the most important factor is the mass of a planet. You see, there is a delicate balance between two competing effects that determine the surface temperature of a planet. First, the more massive a planet is, the stronger its gravitational pull is, and the harder it is for volatile molecules like oxygen, nitrogen, and water vapor to escape its grasp. This means that more massive planets can hold on to their atmospheres for longer and therefore have a warmer surface temperature. Second, larger planets have a larger surface area. And so if we keep increasing the mass of a planet, eventually it becomes massive enough to start pulling itself together into a smaller radius. At this point, the gravitational force becomes strong enough to trap light inside of the planet, heating it up. If a planet is massive enough to start pulling itself together, then the effect of increasing surface area starts to dominate, and the net effect is a decrease in surface temperature. In practice, this means that there exists an optimal amount of mass for a planet to have. More massive planets can hold on to their atmospheres, but they are also small enough to trap light inside of them and heat up. Less massive planets don't trap light, but they lose their atmospheres to space. Earth sits comfortably in between these two extremes. It's massive enough to hold on to an atmosphere, but not so massive that it starts to heat up. Jupiter is the largest gas giant in the solar system, and it illustrates what happens when a planet becomes too massive. It is so massive that its own gravity pulls it together to such a degree that it starts trapping light inside of it. As a result, it is significantly hotter than the Sun. There are other examples of this throughout the universe. Stars, for example, are massive enough to trap light and heat themselves up so much that nuclear fusion occurs. They essentially boil themselves from the inside out until there is nothing left to burn. And once they do, they collapse in on themselves to form white dwarfs. White dwarfs are so massive that they are hot, but they are also small enough that they can't trap light. They essentially radiate themselves to death, slowly fading away into the darkness of space. Now let's switch gears and talk about black holes. Black holes are the opposite of stars. They're small enough that they don't heat up, but they are so massive that nothing can escape their gravitational pull, not even light. This means that as you approach a black hole, the only thing you will see is darkness. But this is where things get interesting, because a black hole is so dense, its gravity distorts space-time. And so as you cross the event horizon, time stops. From the perspective of someone far away, it appears as though you disappear into a black hole. But from your perspective, you feel as though you have stopped moving. Your motion relative to the black hole is frozen in time. This might sound like a party trick, but it's actually a crucial part of what makes life on Earth possible. If it weren't for this warping of space-time, the Sun would be big enough to trap light and heat itself up, but it would also be massive enough to swallow Earth's whole. But because it warps space-time, the Sun can be both as hot and as far away as it is without swallowing Earth's whole. The same is true for every single object with gravity. The strength of gravity depends inversely on the distance from the center of mass. This means that the further away something is from you, the less gravitational pull it has on you. The closer something is to you, the more gravitational pull it has on you. When you stand on Earth, you are experiencing the gravitational pull of all the planet's atoms. Most of the planet's mass is in the core, but that's also where the center of mass is. So you experience very little gravitational pull from the majority of the planet's atoms. However, some of the planet's atoms are on the surface, and you experience the full gravitational pull of those atoms. These are the atoms closest to you. These are the atoms that make up the ground beneath your feet. What happens when you add more mass to a planet? Two things happen. First, the center of mass moves closer to the surface. This means that you experience gravitational pull from more of the planet's atoms, and so you feel heavier. Second, the radius of the planet increases. This means that you are further away from the planet's center of mass. So, although you are experiencing gravitational pull from more of the planet's atoms, you are also further away from those atoms. And so the gravitational pull you experience from each atom is weaker. Interestingly, these two effects cancel each other out exactly. So adding more mass to a planet does not change the surface gravitational pull. The key takeaway here is that the gravitational pull that you experience depends on the distribution of mass around you. The further away the mass is, the less it contributes to your gravitational pull. This means that, as you add mass to a planet, it doesn't grow any heavier. You might think that it should get heavier, but the fact of the matter is that the added mass is distributed further away from you. And so it doesn't contribute any more to your gravitational pull. You might be wondering why this is important. Well, it turns out that there is an optimal range of masses that planets can have. It's massive, and they will end up collapsing into a star or a black hole. It's too small, and they won't be able to hold on to their atmosphere for long. Earth is yet again in a sweet spot between these two extremes. We've seen now that for life to exist as we know it, planets need to be within an optimal range of masses. But that's not all. The planet needs to have the right chemical makeup. There needs to be enough heavy elements present to form a solid surface. But not too many, since too many will prevent the lighter elements from forming an atmosphere. The planet needs to be far enough away from its star that it doesn't boil, but not so far away that it freezes. The amazing thing is that the Earth satisfies all of these conditions. Not only that, but the Moon, which plays an important role in stabilizing the tilt of the Earth, is also within the optimal range of masses. In fact, if the Moon were any further away, it's gravitational. Pull wouldn't be strong enough to stabilize the Earth, and our climate would be so unstable that it wouldn't be suitable for life as we know it. It seems almost too perfect to be believed, doesn't it? planet that is situated just so within a solar system that allows for life as we know it to exist. But this story doesn't end there. Turns out that our solar system is also within the optimal range of masses. Solar systems that are too massive will evolve quickly, destroying themselves in supernova. Solar systems that are too small won't have enough mass to form planets at all. We are truly living in an exceptional time. Everything about our existence is the result of an extraordinary series of coincidences. If any one of these events had played out differently, life as we know it may not exist. Perhaps we are the very, very lucky few who got dealt the best hand in the cosmic deck of cards. I hope you enjoyed this episode. If you did, please hit subscribe. We'd love to have you join the community. Till next time, thanks for watching.